So now that we're done with our unit of surface area, which measures the space on the outside of a three-dimensional object, now we're going to talk about the space inside, which is basically how much a three-dimensional object can hold. And that is the concept of volume. Volume is a space that a three-dimensional object occupies, and the space that it occupies is measured not in square units, but in cubic units, in cubes. How many cubes can fit within a three-dimensional solid? So to illustrate this concept a little bit more, I'm going to show you the kinds of cubes that we're going to be using. Hopefully this comes out clearly, hopefully. This is a cubic inch. Why is it a cubic inch? Because it's a cube, and if I take a ruler and I measure each edge is 1 inch long. Each edge is 1 inch long. This is a cubic inch. If I'm trying to find the capacity, say in this container of cream cheese, okay, I might use cubes that are this big, okay? That's not too big of a container, so that's a practical size for this application. Okay, if I have something bigger like a refrigerator, I might want to use a bigger size cube, and this cube right here is a cubic foot. Not sure if you can see it, okay? The reason why it's called a cubic foot is, number one, it's a cube. Number two, every edge is 1 foot long. If I measure here with my ruler, that edge is 1 foot long. If I measure the height, 1 foot long. If I measure the width, 1 foot long. Every edge is 1 foot long. That's why it's called a cubic foot. Okay. Now that's practical for a refrigerator, something that's bigger than just a cream cheese container. Okay. So going back to my screen. Now that I showed you different size cubes, let me show you some real world applications I was mentioning earlier. Here I happen to have an advertisement for a refrigerator. Notice that it advertises it by how many cubic feet of space is inside the refrigerator. 22.2 CUFT stands for 22.2 cubic feet. And that can be abbreviated 22.2 feet to the third power. And that is read as cubic feet. Here's another real world example of volume. This is a microwave advertised as 1.6 cubic feet of capacity inside the microwave. Obviously, the more cubic feet, the bigger the capacity, okay? Here I have another one that I wanted to show you straight from our Miami-Dade solid waste department. If you have ever thrown away, if you've ever trimmed some trees in your yard or have large objects to throw away, but yet you don't have a pickup truck to drive it to the local dump, you can just lay it outside on your curb. However, it will tell you here how much is allowed. And if you read right here, here's an example. If you're throwing away a wooden fence, you're only allowed up to 3 cubic yards. That means a yard that is, a cube that is 1 yard along each edge, or the equivalent of that much, okay? So notice that these are all real world examples of volume. So how exactly do you find volume of a shape? Do you think, for example, we can just stack in cubes inside something back to back and see how many fit in there, and that's how we get the volume? Okay, for example, let me go back to my camera here and show you an application. Do you think it would be practical for me if I share with my camera? I'm trying to find the volume, say, of this container, how much this container holds. You see how I've already put some cubes in there? Do you think I should just keep filling it in and see how many cubes fit in there back to back with no gaps and no overlaps? That's one way to do it, but that's not very practical, particularly for other shapes that aren't so rectangular along the edges. So I'm going to show you one of the ways, basically, that we're going to calculate how many cubes are within a three-dimensional solid. I'm going to give you a rough version of the formula, okay? So let's say I have this, and I have this shape right here. Let's put all these aside. And I ask you, what is the volume of this? What is the volume? Well, how many cubes are there? There's 3 this way and 2 this way. 3 times 2, there's 6 cubic inches. The volume of that is 6 cubic inches. Now, what about if I add a second layer identical to the first one? Well, how many cubes were there on the first layer? If you look at it really from this perspective, how many there are on that first layer looks, if you look at it from an aerial view, that's just how many squares there are there. Because that's basically how many, what the area is of the bottom. Okay, how many cubes there are in the bottom layer is just 3 times 2, or 6. And then there's 2 layers. Okay, so now we have 12. What about if we add a third layer identical to the first one? Okay, so again, there were 6 cubes on the bottom. Just get the area of the bottom. There's only 1 layer there. 3 times 2 is 6, and then times 3, because there's 3 identical layers. So that's going to be 18 cubic inches. And now if I add a 4th layer, okay, now it's going to be 6 on the first layer. Again, just think about the area of the first layer. It tells you how many cubes there are in the first layer. 3 times 2 is 6. And then how many identical layers are there? There are 4 of them. So the volume of this shape is 6 cubes in the first layer times how many layers there are. Okay? By the way, I'm going to come back to this in a second, but it doesn't matter if the layers are a little bit staggered, as long as the number of cubes at each layer is identical, it won't matter if it's leaning off a bit. That's something called Cavalieri's principle, which we'll talk about in a second. Okay? Whereas with our surface area problems, they were all right shapes. Here they could be oblique. As long as the number of layers, basically the height doesn't change, we're good. So again, it's the number of cubes in the first layer, or basically if you look at it from an aerial perspective, it's the area of the first layer, the area of the bottom, whatever the bottom is shaped like, that tells you how many cubes there are in the first layer, multiplied by how many identical layers there are. And that's basically how you find the volume of a 3-dimensional surface, solid rather. So let me go back to my sample problems and break this down for you a little bit better. With what I just said, this brings us to our formula. Capital B stands for the number of cubes in the bottom layer. But if you remember, I told you before that capital B stands for the area of the base. Well, that's precisely what that is. The number of cubes that are in the first layer will be the area of the base. And then capital H stands for the number of identical layers, which is basically the height of the prism. Let's just say the height of the solid. Okay? So again, the volume formula is capital B times capital H. Capital B tells you the area of the base, which is how many cubes there are in the first layer, and capital H tells you how many identical layers there are. Okay? So some sample problems. Oh, I'm sorry, as I was mentioning earlier, it won't matter if your solid is right or oblique as long as the height is the same and the number of layers at every section is, the number of cubes at every layer is the same. It won't matter if it's right or oblique, the volume will still stay the same. That's called Cavalieri's principle. Okay, so sample problems. If I ask you to find the volume of this rectangular prism here, I'm going to write the same formula for every single problem that we're doing. Area of the base times the height. Capital B stands for the area of the base. Whatever the base is shaped like, that's the formula that I substitute in place of capital B. Here, the base is shaped like a rectangle, so I'm going to use the formula for the area of a rectangle. Note how I have lowercase and capital letters. Lowercase letters refer to just what's happening on one face, but capital letters refer to the whole 3-dimensional object. Capital B is the area of the base. Capital H is the height of the whole solid, okay? Right here, these only refer to the rectangle on the bottom. So that would be 8.4 times 3.5. Again, that will tell me how many cubes there are in the first layer. And then I multiply that by the number of layers, which is 5.6. So multiplying 8.4 by 3.5, that's going to give me 29.4. There would be 29.4 cubes in the first layer, and then times the number of layers, which is 5.6, and that's 164.64 cubic millimeters. Now I know what you're thinking. Some of you say, oh, well, why am I doing all that work? I can just do the formula that I learned in elementary school, and the formula is length. Let me not use that L because that's the L that we use for span height. The formula that we learned in elementary school, is length times width times height. So I can just multiply these three numbers and I'll get the same answer a lot quicker than you will. You're correct. But this formula only works for a rectangular prism, which is what this problem is. If it's any other shape, that formula won't work, which is why I don't like to use formulas that only work one time. Okay? Case in point, this one, a cylinder, though it's not a prism, it is a circular prism. Some people call it that. The base is shaped like a circle. So to get the area of the circle, I'm going to use pi r squared. That would tell me the number of cubes that are on the first layer, and then capital H will be the number of layers that I have. So the diameter here, the diameter was 12, which means that my radius is 6. So it's pi, let me stick to red, which is what I had. So it's pi times 6 squared, and the height of the whole solid is how many identical layers there are, which is 10. So that's going to be 36 pi is the area on the bottom, meaning how many cubes are going to be on the bottom. So if I multiply that, that's going to give me 360 pi cubic feet. If they ask you for exact, you leave it in terms of pi. If they ask you for approximate, you plug in an approximation for pi. The more digits, the better. So it approximately rounds to 1131.0 cubic feet. Okay? Let's step it up. What about if your base is a hexagon, a regular hexagon? No problem. Again, you write down the universal formula and adapt it for whatever the base is shaped like. Here, the base is shaped like a regular hexagon. So we're going to use a formula for the area of a regular hexagon and then multiply that by the height of the whole solid. So for the area of a regular hexagon, they were very nice because they gave me the apothem. The apothem is 10.39. So it's 1/2 times 10.39. There are 6 sides, and the length of each side is 12. So there are 6 sides, and the length of each side is 12. And then the height of the whole object, meaning how many identical layers there are, is 15. So now if I multiply all of these, it would be 1/2 times 10.39 times 6 times 12. The area of the base, or how many cubes there are in the bottom layer, is 374.04. And then that I'm going to multiply by the number of layers, which is 15. And that's going to be 5610.6 cubic meters. Next example is a triangular prism. Don't be confused. It is laying on a lateral face. It is laying on a lateral face. The bases are still the same, the one that there are 2 parallel of. The bases are these triangles, okay? So the formula for the area of a triangle, that's what I'm using in place of capital B. Now the base of this triangle is 9, and the height of that triangle is 15. Capital H is the height of the whole solid. Just because it's laying down, don't let that throw you off. It would be the distance between the bases, which is 12. So go ahead, and if I multiply this, that's going to be 9 times 15 divided by 2. 67.5 would be the area of the triangular base. How many cubes there would be on the first layer, and multiply that by the number of layers, and that's 810 cubic yards. Okay, I've gone over several examples there, okay? Let's try to turn up the heat a bit with a word problem. Yay, word problems. Okay, so with this word problem, Abigail has a cylindrical candle mold with the dimensions shown. Now, she has a rectangular block of wax that she wants to melt down and form cylindrical candles out of them. Okay, so how many candles can she make fitting into this mold if her block of wax is 15 by 12 by 18? Okay, so let's go ahead and find, not drawn to scale, just a sketch to organize my thoughts. Okay, so it's 15 centimeters by 12 centimeters by 18 centimeters. We basically want to know how many of these fit in here, fit inside the block. So let's find the volume of the block first. It's a rectangular prism. So to get the area of the rectangular base, I'm going to use the formula for the area of a rectangle. So it'll be 15 times 12. So if I do 15 times 12, that will tell me how many cubes there would be on the first layer. That's 180. And then that I'm going to multiply by a height of 18. So 180 times 18, I have 3,240 cubic centimeters of wax in this big chunk of wax that is purchased. Now let's find out how much each candle will occupy, will take up, how many cubic centimeters. So the volume formula, again, the universal formula, base area times height. The base is shaped like a circle, so we're going to use the formula for the area of a circle in place of capital B, okay? In place of capital B, we're going to use the formula for the area of a circle. Okay, so the radius, I'm sorry, I wasn't paying attention. I was thinking of something else. It's pi r squared. My apologies. Okay, so the radius of this circle is 3.4. So it's pi times 3.4 squared. And then that I'm going to multiply by a height of 6. Now here's the thing. You have even though this has pi, the block is not in terms of pi. So we're going to have to plug in pi whether you really like it or not, because you have to get it something to compare it to a non-pi unit. So we're going to have to do pi times 3.4 squared. And that's going to give us a huge number, which we're then going to multiply by 6. And that's going to give us approximately 217.9 cubic centimeters for each candle. So this is the number of total cubic centimeters of wax that you have. Each mold takes up this much. So if you divide 3240 by 217.9, you're going to get 14.869 ... candles that you can make. But you can't make a fraction of a candle. So how many full candles can you make? You can make 14 candles, and you're going to have some left over. It's not like the paint application where you have to round up to buy the next gallon of paint. This is how many full candles will you make. Okay, so it'll be about 14 full candles. Now I know they said to round to the nearest tenth. Well, if you say to the nearest tenth, then it would be 14.9. But in terms of the real world application, it would be 14 candles that can be made. Okay, so you want to do one more? I'm going to show you one more. Okay, another real world application is in concrete. In Florida, you see lots of people have these driveways, and these driveways are really nice. They're made out of poured concrete, and poured concrete is sold by the cubic yard, So the issue is, how do they calculate by the cubic yard if these things are obviously not shaped like cubes, and they're certainly not 1 yard along each edge? Well, what they do is they convert. So I'm going to give you an example at this website. If you go to this website, what you do is you enter the width, the length, and the depth of the slab of concrete that you're going to pour, and it will calculate the number of cubic yards. Okay, So usually these, going back to this picture that I was showing you a second ago, usually these are 4 feet by 8 feet by 4 inches deep. Okay, so going back to that website, okay, 4 inches is the depth, okay, the length is 4 feet, and the width, actually usually it won't really matter in this case. Okay, usually it's 8 by 4, as long as you have 4 inches on the depth, 8 by 4. And let's see how many cubic yards that calculates into. Here they told us that's 0.4 cubic yards. Now, how did they get that number? I will show you how they got that number, okay? You gotta be really careful when you're converting, okay? If it's sold by the cubic yards, you want everything in yards from the beginning. Unfortunately, it's sold by the cubic yard, so we have to convert to a bigger unit, which means we're gonna have some fractions, okay? Hopefully you don't get scared. How many inches are there in a yard? There are 36 of them, okay? So if I take the number 4 inches and I want to convert that into yards, that would be 4/36 yards, okay? Let's convert each of these feet into yards for the length. How many feet are there in a yard? There are 3, okay? So we have to divide this by 3. So this is 8/3 yards. And now let's convert the last dimension. Okay, this is 4, divide that by 3, that's 4/3 yards. If you don't want to deal with decimals, just keep them all as fractions, okay? So now, if I want to get that volume, again, each of those slabs, not drawn very well, I apologize, okay? So we're going to have here, this is 8/3, this is 4/3, all of these are in yards, and this is 4/36. So it would be 8/3 times 4/3, and then that answer times 4/36. How do we multiply fractions? Just multiply horizontally if you can't cross cancel. That'll be 32/9 times 4/36. I prefer to cross cancel. Cross canceling makes things easier, but I know many of you are already freaked out because we have all these numbers, these huge numbers. Just multiply straight across, guys. 32 times 4 is 128. On the bottom, 9 times 36 is 324. And guess what you get when you divide 128 by 324? Approximately 0.40 cubic yards, which is exactly what they said it was going to be. Okay, so that application, hopefully it didn't scare you, but that's a real world application of volume. Okay, so that should be enough to get you through tonight's homework. And next time we're going to go on to pyramids and cones.